Okay, guys, 3.2 continued. The next thing I want to talk about is the remainder theorem, which is included in 3.2. This is also going to help us with this sections coming up. But the remainder theorem tells us if the polynomial f of x is divided by x minus k, so this x minus k, that's like your g of x that we've been using, okay? They're just saying, okay, x minus k. Then the remainder is equal to f of k, okay? And you might be wondering, okay, well, why is that relevant? Well, it's really going to be helpful in 3.3 and 3.4, trust me, okay? So let's see how we can use this. Example, use the remainder theorem to find f of k. Now, if this right here is my f of x, okay, I forgot to write this is f of x, okay, of course we could find f of k if k is equal to 2 by just doing, okay, well, f of 2, and then just plug it in for x, right? So you're saying, why are we not doing that? Well, we're going to do the division because when we get to 3.3, it's going to help us because we're going to be able to basically kill two birds with one stone. We're going to be able to figure out, okay, is it a 0? Okay, so remember a 0 is whatever would make it equal to 0 because that's very useful, right? When we're looking at these graphs, we know a real 0 corresponds to an x-intercept, okay? And if it is, it'll give us kind of the next parts of the problem. That's what I'll say for now, okay? So it's actually quicker than doing this whole plug-in thing, okay? So what I'm gonna do is I'm gonna say, okay, well, if k is equal to 2, that means my x minus k is x minus 2, okay? According to the theorem. So here's what I'm gonna do is I'm gonna do x minus 2 into the 2x cubed minus 3x squared minus 5x plus 4. And if I do this, the remainder theorem tells me that the remainder that I get from the division is what f of 2 is. Okay, once again, you may wonder, okay, why is he doing this? It will be clear in the next section. Okay, so of course, what's quicker is I'm going to use my synthetic division. So if I look at this, okay, what's the 0 of that? The 0 is 2. And then I'm going to do the same thing I've been doing. Okay, with the coefficients, and I'll do my synthetic division. This is a lot nicer than the long division. That's 1, that's 2, that's -3, that's -6, and that's -2, okay? Now, here's the thing, okay? When I did that division, I have this, I have 2x squared plus x minus 3, and then I have plus -2 over x minus 2. Now, what's going to be useful next section is I'm going to want this, which I wouldn't get by just doing this, okay? So I'm going to get this, but the big one I'm interested in this case is this -2, okay? So the -2 tells me that f of 2, if I plug 2 in to this polynomial, I will get -2, okay? And that's exactly what we're looking for now, okay? Now, we're going to be interested in the next section when this is 0. That's really what we're going to be interested in. And speaking of getting a remainder that gives me 0, let's look at this example. Decide whether the given number k is a 0 of the polynomial function. Remember, a 0 is just a number you plug in for x that makes the whole thing equal to 0. We know that's relevant with the graphs because real zeros correspond to those x-intercepts, right, that we talked about in 3.1. If not, give the value of f of k. So this is literally basically the exact same thing. We're just trying to see, okay, is it a 0? Does the remainder come out to be 0? Okay, so when I look at this, I'm going to just do my synthetic division. So this is just like doing x. This would be, since k is -3, if it's x minus k, it would be minus -3 or x plus 3 into x cubed plus 2x squared minus x plus 6. Okay. And I'm going to go ahead and I'm going to do this division, okay? So I'll do it as synthetic division. I guess the 0 is -3. And here's the thing to notice that'll save us a little time. Notice that k always matches what I put in the box, just like in this last problem. We said f of 2, that's what I put in the box. So that can save you a little time. So I have -3 and then all my coefficients. So I'll bring it down, I'll multiply it. -1, 3, 2, -6, 0. So since the remainder is 0, that tells me that f of -3 is equal to 0 by that remainder theorem. So what's the answer? Yes, -3 is a 0. Let's look at B. Oh, hey, remember those, the imaginary numbers. Well, actually, it's complex. It has an imaginary part, though, right? So same idea. So since we know K is always the thing that goes in the box, I'll go ahead and do that right away. So 1 minus 2i, and then my coefficients. I better leave a little room. Okay, so you can want to remember way back in chapter 1 when we dealt with these. Okay, bring down the 1, multiply. So that's going to be 1 minus 2i. Okay, now I really should have left this lined up here, but I have -3 plus 1 is -2. And then I don't have any i's, so I'm just left with minus 2i. Now I got to multiply these to figure out what to put here. Remember how to do that? Let's go off to the side. 1 minus 2i times -2 minus 2i. Remember, it works the same way as with x's. I just know that I squared is -1. So this is going to be -2 minus 2i plus 4i plus, right, because a negative times a negative, that's going to be 4i squared, okay? So that's -2 plus 2i, okay? Plus 4 times -1, that's -4, so -6 plus 2i, essentially, okay? That's what goes right here, -6 plus 2i, okay? So what do I get from that? Well, looks like I'm going to get a -1 plus 2i, okay, which is not 0. So I know it's not a 0, okay? Just want to look over one more time just to make sure everything got put in right. It says -2 minus 2i, -2, so I got -2 minus 2i plus the 4i plus the 4i squared. Yep. So that's -4. So yeah, that's definitely -6. Okay. So that looks good as far as I can tell anyways. All right, good. So what does this tell me? This tells me that f of 1 minus 2i is equal to -1 plus 2i. Well, that's not 0. So that tells me that no, 1 minus 2i is not a 0. All right, and that does it for 3.2.